what are examples of stress concentration? Or why would that even happen? So stress concentration is where you'll have high levels of stress, and you will have that whenever the geometry changes suddenly. So for example, if you look at a board, okay, it's got some, let's say, threading. This is the head. These are the threads. There are two places where there's a change in geometry, this point and this point. Geometry changes abruptly. Okay. So this thing leads to stress concentration. Okay, so the stresses at that point where the geometry changes are much higher than what you would expect using the calculations we've done so far. So if there's, for example, if this bolt is subjected to a force P, then you would say that the stress is P divided by the cross-section area, right? But because there is that change in cross-section, the stress will be much more than P divided by the cross-section. There's a stress concentration factor which you need to put in the formula for stress in order to figure out the exact stress over here, where the geometry changes. Okay, the other examples of places where you will see stresses are transmission shafts, where there are keyways, key seat. So this is a trick which is used to keep two shafts together. There are grooves in the shafts and in the two mating shafts, and then you put these keys so that two pieces can hold on to each other rightly. So that would cause stresses. There would be in shafts with shoulders. So what you do is when you make use shafts in design, you don't have like a shaft of uniform diameter. You'll see that at some point you'd have to increase the diameter at some places just to accommodate elements which have bigger or smaller holes. And those changes in geometry causes a stress concentration. Okay, so shoulders on shafts, grooves, holes, notches, cause stress concentration. So you do this for a purpose, right? You have keyways, key seat because you want to mate shafts, but it introduces stresses, and those stresses can cause premature failure. So on the one side, you need them because that's how you'll mate two parts. But on the other hand, it leads to stress concentration. So the best way to mitigate this problem is to figure out what the stress would be if you have these keyways, grooves, and sort of have the dimensions such that they would not really cause the stresses to reach an extent where the material will just break, right? And so this section will not get into the design of elements, but it will tell you how to compute the stresses when there's a change in geometry. And the approach we follow is basically an empirical approach that they have taken these specimens and loaded them and then use strain gauges to figure out the stresses. And then there's a table which is generated, and that table can be used to figure out what the stress is. The other way to do this is to use a software like finite element analysis, which you might have used. The problem with finite element analysis is that it's based on finite elements. And when you have stresses, they typically can go to a very big value, a very large value. And the finite element analysis cannot compute the stresses, especially when they blow up. So finite element analysis actually fails to predict stress concentration. It does to an extent, but it can't really give you the exact stress. So the method which people use is there's a technique called photoelasticity, which is basically making a specimen of plexiglass. Maybe it's not plexiglass, it's material which is translucent, and then they load it, and then you get this nice fringe patterns, and those fringe patterns tells you something about the loading. They use the same thing to design landing gears for planes. Anything which they expect is going to have stress is going to be tested with a technique called photoelasticity, not using finite element. But finite element is a good way to get started. Okay, so we'll use this approach where people have done this experiment on the part, and they've given us data, and we'll use that data to compute the stresses. So this is how it is done. We're going to introduce a factor, a stress concentration factor. And then we'll have two names, one for shear and one for normal stresses. So KT and KTS. So KT would be sigma max divided by sigma 0. And KTS, which is for shear, is the shear stress max divided by shear. So what are these values? Sigma max and tau max are the stresses at the discontinuity which is typically measured, right? You use a strain gauge to measure them. And sigma 0, tau 0 are the nominal stresses in the absence of the discontinuity. So these factors depend only on the geometry. They do not depend on the material. So if you have a different material, steel versus aluminum, those KT, KTS will not change. So what we'll be doing is, depending on the geometry, there is a table which gives you, in this case, there's a figure, a plot, which gives you KT for different geometries. So knowing KT from that question, yeah. The tau is it should be tau 0. Not nominal stress. So the KT, KTS comes from the table I'm going to show you. Sigma 0, tau 0 is something which you compute in the absence of that discontinuity, which again, I'll show you how you can compute that. And then sigma max and tau max is what you're going to use as the actual stress. So when you're designing something, your stresses are going to be sigma max and tau max. Obviously, sigma max is going to be greater than sigma 0 because the introduction of the discontinuity introduces stresses. So KT is always, and KTS is always greater than 1. Okay, they are greater than 1. Okay, so what we are looking at is the book, full appendix. Let's search for, there it is, A15. Charts of theoretical stress concentration factors, KT, and then this one, A16 is a specific section. Let's look at A15, 1034. Probably be some. Okay, A15, let's just go to A15. This. I think it starts here. Okay, so here's an example. Now, if you assume there was no hole there, okay, and you loaded that specimen with a force F, and the stress on that, on the produced in that rectangular bar is going to be sigma 0 equals F divided by A, where A is the cross-section area. So it is, in this case, it's going to be the W, which is shown there, and the thickness, which is not shown. It's in the plane of the paper. So W times T. Right? So that will be how you compute sigma. But because there is a hole there, what you'll do is you will use A as, in this case, maybe it's best to draw this. So I'm just cutting this at the hole. And now I have to compute the area of this part. And you can see that that area is W minus D, which is now going to be the height of this minus the hole, right, times the thickness. And that's how you get A equals W minus D times T. So that's sigma 0. But remember that KT is sigma max divided by sigma 0. So given the dimensions, W is the width and D is the diameter of the hole, you can then compute what KT is just by looking at the figure. So for example, if it's 0.4, then KT is going to be, I don't know, 2.25, I guess. And then you use 2.25 here, which is known. And then sigma 0 is known because you know what F is, supplied load is given, and the cross-section area comes from geometry. So sigma 0 is known, and then you can find sigma max. That's the stress which will show up right here. And that's clearly more than the stress you would have without that hole. Yeah. T is going into the pages. So let's try it with this. So hard to do. This is T. And then this is W minus T, that is minus the. Okay, so there are tables for various things. There is, this is axial loading. If you have the same specimen subjected to a moment, then you'd use that table. So now it not only depends on the ratio of D divided by W, but also depends on the height. In this case, that would be the thickness. That would be for axial loading, but note that there's a fillet, sort of a fillet, groove on top and down. Here's one for moment. Different geometry. That's a fillet of radius R. Moment. Different type of shaft, subject to force, torque, moment, bending moment, and just keeps going. So these are the more common geometries which you'll see when you have elements. So what you need to do is just figure out what that KT is based on this. Okay, so what we'll do is the best way to illustrate how these things are done is to solve a problem. So let's do just that. And hopefully it'll be clear how to compute the stress concentration. Okay, so let's start. So a 2 mm thick bar So this dimension is in the plane of the paper. It's the thickness is 2 mm. Is loaded actually with a constant force of 10 kilonewtons. The bar material has been heat treated and quenched to raise its strength, but as a consequence, it has lost most of its ductility. It is desired to drill a hole through the center of the 40 mm force face of the plate. It's at this hole. To allow a cable to pass through it, a 4 mm cable is sufficient for the cable to fit, but an 8 mm drill is readily available. Will a crack be more likely to initiate the larger hole, the smaller hole, or the fillet? Okay, so I guess there are three things we need to consider. One is we just put a cross section, a line there to indicate the cross section. So let's say that this is A prime. This one, let's call that B prime. Okay, so we have three scenarios. The larger hole, so you can drill a larger hole because you have a drill available, which is of 8 mm, right? But a 4 mm hole will do it because the purpose of this is to have a cable pass through it. So we have two choices. Either we can have a 4 mm hole or an 8 mm hole. It's cheaper to give the 8 mm hole because the drill is available. If it's 4 mm, then you need to get a drill which is of that size. So both these scenarios will lead to different stresses. And we want to figure out basically which of those would have lower stresses, right? But then there's another place where you could have a stress where it could fail. It's the fillet at BB. So this is at A prime, A prime, or the fillet with R equals 1 mm. So here's the rationale behind this question. There are three places where there's going to be stress concentration. One of them is going to have the maximum stress, clearly, right? Let's say that the maximum stress is at the section B prime, which means that if you apply more load, more than 10 kilonewtons, it's probably going to fail at B prime. And so we don't care what the size of the hole is at A prime, because the critical part is B prime. And so we'll just go with the 8 mm hole. However, if we see that the 8 mm hole is going to be the most critical part, then we should say, no, we cannot use the 8 mm drill. We need to go and purchase or get a 4 mm drill and use the 4 mm hole. So your design decisions are now based on the stresses which are created due to these geometries, and the maximum stress is the one which will determine your next step. Either you'll go for a 4 mm hole or an 8 mm hole. So clearly we need to compute the stresses for those three cases, which we'll do. And then we'll compare and see which of them was the maximum one. So let's get started. Let's compute the stresses due to the 8 mm hole. Okay, so the stress at A prime due to, I guess, well, let me just write the formula first, it's easier. KT is what he'll use because it's not shear. It's sigma max divided by sigma O. Sigma max at A prime is going to be KT times sigma 0. Okay, so I need to find sigma 0. So the best way to do this is to just look at the corresponding figure in the appendix it'll actually give you everything. It'll give you KT, it'll also give you how to compute sigma 0. If you don't know how to compute sigma 0, you can use that formula I just told you about. It's P divided by W minus D times T, which is also in that. What I did was actually took a screenshot of that table. I'm going to paste it here. Okay, so that's what we want. So we need the ratio of D divided by W. That's going to be, the D is the hole diameter, so that's 8. W is, you can see here, it's the width, that's 40. So 8 divided by 40 is 1/5 is 0.2. So go and look at what's KT at 0.2. Okay, it looks like it's approximately at midway between 2.4 and 2.6. So it should be 2.5. Let's use 2.5. Okay, then sigma 0 is the force divided by W minus D times T. So P is 10 here. W is 40 minus 8 times thickness. It's 2. And just to be safe, let's just convert everything to SI units. So the force is in kilonewtons. So I need to multiply that by 10 raised to 3. And then everything below is in mm. And to convert mm to meters, I need to multiply by 1e negative 3. But I need to do that for the W and W minus T, and I need to do it again with T. So I need to multiply 10 raised to negative 3 twice. One is for this. You know what? Let me make it clear like this. So 40 minus 8, that's W. And then T, it is 2 times. Okay, that's why it is twice. One for W minus D and one for T. Okay, there's a lot over there. But let's now find. So the sigma comes out to be 156 megapascals. So sigma max at AA prime is KT times sigma 0. KT, we computed that to be 2.5 times 156, 390 MPa. Okay, so that's our first stress. The second one, we'll find the stress, compute the stress at AA prime due to 4, and then okay, so we do the same thing. We need to compute D divided by W. The D is 4, W is 40. So this is 1/10, which is 0.1. So 0.1. That doesn't quite look like it's midway. It looks like it's slightly below 2.7. So 2.65. We could use 2.65. Yeah, I use 2.7, but 2.65 is absolutely fine. Let's just use 2.65. So for a problem like this, as long as you are anywhere between, 2 points, you clearly don't write 2.6, you don't write 2.8 because it's not one of those. But if you're anywhere between, I guess, 6, 5, and 7, it's considered correct. Okay, you don't have to get the exact value. So let's say 2.65. Okay, now let's compute sigma 0. The same formula applies. It's P divided by W minus D times T. P is 10 kilonewton, so that's 10 times 10 raised to 3. W is 40 minus D. D is 4. And I convert that to meters by multiplying by 1 e negative 3. And then thickness is 2, which I multiply again with and the negative 3. Okay, that comes out to be 139 MPa. Yes. Yes. And so let's compute the stress now. Sigma max at AA prime is KT sigma 0, which is 2.65 times 139. $368.35. So just to distinguish this, maybe we just have to put the actual. So the stresses look like they're the same, but they're for different geometries. Like let's just put 8 here. Then 4 mm. So it's interesting that the stress due to the 8 mm hole is greater than the stress due to the 4 mm hole, even though the stress concentration factor for the 4 mm hole was greater than the stress concentration for that one was 2.5, right? So 4 mm hole introduces a bigger stress concentration factor. However, the stresses in this case are greater, and that's because of this area. The cross-section area is different for those two. And I think that's kind of interesting. Okay, so we've computed the stresses due to 1 and 2. Let's compute the stress due to the fillet. Yes, due to fillet. Okay, so let's look at the geometry. And we need to go to the table or that appendix and figure out if there's a geometry like that with the fillet. And then we just take that geometry to compute KT for that geometry. So what I did was I actually picked that, I took a screenshot of that table, and I'll put it here. Okay, so we need to compute these ratios, capital D divided by small d and small r divided by d. We just go back to the problem and see what those are. So capital D is, yes, it's 40, and then small d is 34, and r is 1. Small d is 34, and r is 1. 30, 34, 1, that's right. Okay, so let's compute d divided by d. It's 40 divided by 34. That's 1.18. Small r divided by d is 1 divided by 34. That is 0.026. Now, I can pick one of the two. So let's just start with, say, this one, 0.026. So this is r divided by d. This looks like it should be halfway. This is probably 0.025. So really, I cannot distinguish 0.026 here from 0.025. So let's just stick with that. And then I need to go to capital D divided by D of 1.18. But we have 1.1 and we have 1.5. I mean, it's probably somewhere between here and, so there's probably a curve here which is missing. So in such a scenario, I would say you can choose anything in this range. It should be fine. Okay, so anything between 2 point, whatever this coordinate is, all the way to 3. What I did was I just decided to go with 2 point, this coordinate of this point. This is 2.4, it's halfway. I just chose 2.5 just to make round numbers, but as long as you're in this range, you should be fine. So I need to compute D, capital D divided by small d. That's 1.18. So this is 1.5, this is 1.0. And so it has to be somewhere in between. So choose anything you like. I will just choose 2.5. So KT is 2.5. Sigma 0 is going to be the force divided by, so it's the stress here. So that will be T times T, that's the cross-section area. So 10 times 10 raised to 3 divided by D, which is 34, 10 raised to negative 3, times the thickness, which is 2 times 10 raised to 3. Okay, so doing the calculations gives me 147 MPa. Okay, the last thing left is to find sigma max. This is at B prime is KT times sigma 0. So it's 2.5 times 147 comes out to be 368 MPa. That's so close to the other one. Okay, so let's summarize all the stresses we've computed so far. out of space. So 368 due to this one, then there is 368.35, 4, and then 390. So let's just put a summary here. Sigma q to the 4 that was my first one, 390 MPa. Okay, so this is the max stress. This is probably the min stress. They're so close actually. So I really won't take that 3 is smaller than 2. Remember, we made that assumption on KT. We took the lowest KT. So if you want a less conservative design, you probably want to ramp up the KT. This was built on 2.5, which came from here. But really, the point should lie somewhere here. So you might want to go back and fix that, make it 2.6 or even 2.7, and then compute it, because that is an approximation. So anyway, if you assume that all these calculations are right and our values are right, then we clearly see that the maximum stress occurs at 8 mm. And so that 8 mm drill, which we're using, is no good. We should not drill an 8 mm hole. We should go and get a 4 mm drill and use it in this particular specimen, because that one has a stress which is similar to the stress at BB. And so given a loading condition, it will fail at the same time, in this case, as BB prime. That just increases the amount of stress this particular specimen can take by using the 4 mm hole.